everyone for joining us on this fine Wednesday. Appreciate you guys giving up your evening to come and listen to Katja on her talk. Definitely been very excited about this one, like having this in the agenda. Really can't wait to sort of let Katja deep dive into generative AI and share all of her wisdom around it. So I'm just going to give you a bit of an overview of the agenda before we get started. First up, we'll have Katja, who will be giving us a bit of a presentation for about approximately 30 minutes. Following that, we'll also have like a bit of an engaging Q&A session with Ekaterina. And then adding to an exciting twist, we'll be hosting a competition where you stand a chance to win some free courses, which is very exciting, which will be sort of revealed towards the end. And then, yeah, our special guest tonight is Ekaterina, also known as Katja. So you might hear me refer to her a little bit like that this evening. She's a deep learning scientist from Nvidia. So she's bringing expertise in the field of generative AI and has got quite extensive experience in this field. And then the talk this evening will be about multimodal generative AI. And how we've seen some significant advancements enabling the creation of like realistic images, videos, audio. However, like due to the complexity of these models as well, we need to understand how they function, how to apply them in practical settings, as it can be challenging. And during this talk, Katja will shed some light on the inner workings of multimodal generative AI by discussing key concepts and techniques used in her development. And she'll also explore various applications and use cases of this technology. So the talk is really intended for anyone interested in the current state of AI and its potential to produce realistic and immersive multimedia experiences. Now, without further ado, I'll pass the virtual floor over to Katja. So Katja, if you want to start by sharing your screen, we can dive right into it.
Thank you, Finlay. Happy to be here. So I'll start sharing my screen now. You should be able to see my screen now. Could you confirm, Finlay?
Yeah, we can see it all okay. Thank you, Katja.
Perfect. So nice to meet you all. And as Finlay has introduced already, I will be talking about multimodal generative AI today. And I'm a senior data scientist, and if there are any data scientists who joined this call today, I can guarantee I know how you feel this year. At least that's how I feel this year. While some of us are still tweaking parameters of convolutional neural networks and choosing what type of parameters to put there, the huge wave or tornado of new generative AI techniques is sweeping out everything on its way and even making some jobs obsolete. But before we continue with generative AI, let's take a look into the retrospective. So before we had the huge array of specialized architectures. We had architectures for image processing, like convolutional neural networks. We have GANs for image generation. We had recurrent neural networks for text and speech processing, and reinforcement learning for robotics. And what's special about these architectures, this approach, is that, for each of these architectures, you would need a specialized data set, like, for example, for CNNs, if you want to train a cat detector system, you would need thousands of cat images, which would be then annotated by a human observer, and then you would train this network. And then in the end, we will get a deep learning model, which is very good at doing one and only task in detecting cats. And of course, you can extend like to different classes, but then it will be still limited to these classes only. And you can imagine this is not very sustainable, because if we want to create something like artificial general intelligence, you cannot just label the whole world of data. And I believe that a sustainable solution has been found, and it is multimodal generative AI, or multimodal large language models. And in this approach, we basically have, in the core of this technology, we have some huge model, a large language model based in a transformer architecture, which has been trained on large scale of data, like to the scale of the whole internet. And this model has learned the data from the internet and is able to generalize on new unseen data. Of course, this is more sustainable, and you don't need to label that. It has to work in the unsupervised way. And there's already evidence that these approaches are already here, and that they work and that they're useful. So in this paper, Sparks of Artificial General Intelligence from Microsoft, they were able to show that GPT-4, GPT stands for Generative Pre-trained Transformer, and it's a multimodal architecture by OpenAI. They were able to show that this GPT-4 architecture is able to perform zero-shot learning tasks. And by zero-shot, we understand the tasks the model haven't been specifically trained on. It is able to perform zero-shot learning tasks with the accuracy of 82%. And 82 is a really big number. And it also already indicates that these approaches are already very useful. Another great example, so here it's taken from the GPT-4 technical report. So they have shown that the GPT 3.5, also known as ChatGPT, which is not multimodal, was able to perform quite well on some of the exams, like environmental science, and it didn't perform that well on exams like calculus, some other exams. However, when adding some extra modalities, and in particular image modalities, they were able to achieve much better performance. So it's no longer incremental, it's a substantial improvement. And here's another good example. They have shown this image I'm showing you on the slide to also GPT-4. And they've asked it, what is funny about this image? And as you can see here, we have a mobile phone which is charged by something which looks like a VGA connector. And you all know that you typically don't charge phones with a VGA connector. And apparently GPT-4 also knew that, and it hasn't been specifically trained to detect phones, it hasn't been specifically trained to detect VGA connectors, and yet it is able to understand that, and it's also able to reason that it's not usual, and that's why it's funny. So even a year ago, I wouldn't imagine AI models being able to reason about humor. So it's a really big breakthrough, I think. And basically what we are observing that multimodal generative AI is changing every industry. And in my role, I work a lot with customers and partners from different industries. So I have the luxury of learning about the use cases, about the demand for the technology. So here I've collected like a few of examples, what I see in the different industries. So in education, for example, there we can see that multimodal generative AI could be used for personalized learning, where we observe, for example, learning patterns of an individual student, and then we can tailor learning plans accordingly. Or, well, generative AI can be also used to create some enhanced materials, to supplement text information with visual data, with diagrams and some images in order to help better understand some complex concepts. And generative AI can be also used for brainstorming. Like, for example, when I was doing my PhD, I had to write quite a lot. And I remember this fear of big white paper where you don't know what to write there. And now things like writer's block are a thing of the past, I believe, because you can always ask a Gen AI model to give you some seeding ideas, and then you can further expand on that. In healthcare and life sciences, generative AI is used for drug discovery and precision medicine. Precision medicine is also like when you get data from a specific patient, and then you create some treatment plans accordingly. And by such data, we can understand like image data, but also patient records, family history, some scientific literature can be also used in these approaches as well. So all this combined together can be used for precision medicine. In genomics and protein structures, we also rely on multimodal generative AI. But also there is an interesting use case some researchers are working on is generation of synthetic organisms and organs. Maybe in the future we'll all easily get replacement of some failed organs by some synthetic one. In design and engineering, we see also generative AI is largely used for brainstorming, for suggestion of some ideas, then also for synthesizing complex solutions and for automating mundane tasks. And another use case which I see high demand for is generating parametric designs. One such example would be you have a CAD model of some object and you would like to modify this object accordingly to the environments it will be used in. And you can take the environment information, you can feed it into the model, and then you will expect the model to adjust your CAD model accordingly. In marketing, media, and entertainment, we also see many use cases like personalized advertisement, where like the content will be created for you specifically. Although I must admit, I find it a little bit creepy. Well, you can also think of interactive experiences where you as a user will be playing like VR games where non-playable characters will interact with you. And in fact, we at Nvidia have partnered with one of the startups and have created a really nice demo of such an interactive experience. So let me share it with you. I hope you will be able to hear the sound. Let's see.
We're thrilled to showcase an immersive and dynamic interaction between a player Kai and a non-playable character named Jin. This captivating ramen shop scene was created by Nvidia using the latest RTX rendering technologies. Nvidia collaborated with Convey, an Nvidia Inception partner, to showcase how developers will soon be able to use Nvidia Riva, Nemo, and Audio to Face for AI-powered speech, conversation, and animation. These models were integrated into the Convey Services platform and fed into Unreal Engine 5 and MetaHuman to bring Jin to life. Please take a look.
Hey, Jen, how are you?
Unfortunately, not so good.
How come?
I am worried about the crime around here. It's gotten bad lately. My ramen shop got caught in the crossfire.
Can I help?
If you want to do something about this, I have heard rumors that the powerful crime lord Kuman Aoki is causing all sorts of chaos in the city. He may be the root of this violence.
I'll talk to him. Where can I find him?
I have heard he hangs out in the underground fight clubs on the city's east side. Try there.
Okay, I'll go.
Careful, Kai.
I think it's really fascinating. I love watching this. Another good example how generative AI can be useful in virtual environment settings. So here I'm showing you a screenshot from our Omniverse platform, and you basically can use it to together with ChatGPT in order to create layouts of the rooms. So let me show you another demo.
By now, you've probably heard how exciting GPT-4 is. Of course, Omniverse is the best place for building tools for 3D generative AI, RTX rendering, and simulation. So it makes sense to combine the two and see what we get. We already have partners building amazing tools, so let's start off by using one from SyncTwin that makes floor plans like this one. We built our own extension that lets us tell ChatGPT the type area we want this to be, All we have to do is draw around the area based on SyncTwin's blueprint, and it builds the floor. It not only uses that description, but also uses deep search to pull in the perfectly suited SimReady library asset. If we want to change one of the items, we use another extension that lets us pick through the search result that deep search gives us. All this using the combined power of GPT and generative AI tools in Omniverse. While we're at it, let's use ChatGPT to write this script.
I didn't use ChatGPT to write my script. So what is generative AI? By generative AI, we understand a type of AI which can create new content by learning patterns from existing data and then using that knowledge to generate some new unique outputs. And in the core of this technology, we have a model, also known as large language model or foundation model. By foundation model, we understand a model which has been pre-trained on various sources of data. Well, it can be also trained in text, but it can be also expanded in the multimodal scenario to images, audio, 3D, and structured data. And once trained, this model is good at performing one and only task, and this task is predicting what comes next in the text. And we can then take this model and we can customize it. And by customizing it, we can adapt it to perform different downstream tasks. Such tasks could be like code generation, translation like from different languages, summarization of text, summarization of video, image and video captioning, sentiment analysis, and like typical computer vision cases like object recognition, for example. And in order to, what do we actually need to pre-train a generative AI model, or in other words, to create it from scratch? We need a large amount of data, and as I've already mentioned, like to the whole scale of internet that large, we need billions of parameters, and well, it is also necessary to reflect as much as possible in your model, and to make this model generalizable to any kinds of zero-shot learning tasks. And we also need unsupervised learning, because as I mentioned, we cannot label the whole world of data. And so far what I've told you can also apply for like language and text, but if you focus on images, what is actually the difference for image and language generation? So in language, as I mentioned, we train data on text, and then our task is to predict the next word. In images, we can use textual prompt in order to prompt our model, and we can create an artistic image, a new image which never existed before. And for that, we need to rely on some additional technique called diffusion. And in the rest of my presentation, I will tell you how diffusion technique works. What have motivated me to learn that was this app called Lensa AI, where you can upload a dozen of images of yourself, and it will then create nice artistic portraits of yourself. So I found it super cool, and I wanted to learn how it works. So now I know. But generative AI has been here already for some time, generative AI for images. And well, it dates back to 2018, where when Nvidia has presented their style gun approach. And I wasn't working at Nvidia back in the day, but I was traveling to the CVPR conference where this paper has been presented, and I remember how fascinating it was. So this style gun was able to create like very natural human portraits, although these people never existed before. And they further expanded the approach to Galgan to generate beautiful, realistic landscapes. And then the new wave of generative AI based on latent diffusion has appeared, like DALL-E by OpenAI has been also introduced last year. Then we have Midjourney, for example, who took it to the very new level of quality. Like the results you get from Midjourney are really very fine and like have some really artistic qualities. We have also Stable Diffusion, and the creators of Stable Diffusion, they have revolutionized that in the sense that they took the model and they've published it on Hugging Face. And it basically allowed many researchers from the world just experiment on that, expand on that, and do even more research in this area. And now we're entering the era where static images are not enough. So some approaches emerge which work with 3D content creation from textual prompts and video content creation from textual prompts. So it's really exciting. It's an exciting time, and we'll see more and more of it coming in the future. You may wonder, can I actually fine-tune the model like a generative AI model for image creation? And the answer is yes. So you can do fine-tuning. So basically 2 types. You can either bring your own object in the generation pipeline, or like a portrait. If you want to generate portraits of a specific person, you can do that, or you can also fine-tune to do style transfer. So for that, you need some images in the specific artistic style, and then you also fine-tune the model for the artistic style. And I've done such a fine-tuning experiment myself as well. So I used a model called textual inversion, and I've trained it on a data set consisting of 8 images from the Lion King movie. I just went online and I just downloaded this 8 Lion King images. Unfortunately, I'm not allowed to show you them because I don't have the rights to these Lion King images. But my whole data set consisted of only 8 images. And I ran the training for 1 hour on my A6000 GPU, which I have at home. And I've prompted the model to generate me images of a Pink Panther in the style of Lion King, and that's the result which I got. And you can see that some of them are funny, some of them have like 5 legs or funny tails, but this style is definitely there. And I've tried it before and after, like without the fine-tuning, and the style was clearly there. So it was really fun. And yeah, if I would have trained for a longer time, maybe I would get even a better result. So how does text-to-image pipeline work? And the keyword here is a pipeline. It's not a single model, it's a pipeline of several models, and there's 3 major components to it. So the first one is a clip. It's a text encoder and image encoder here, which basically the goal of clip is to unify the embeddings. The embeddings are the representation numbers between images and text. And the second part is the image generation part, which consists of 2 components, which is autoencoder and the unit architecture. And in the following slides, I will explain you how this pipeline works. Let me go through them one by one. And the first one is unit. And those of you who work in data science for long enough, you remember it as a perfect architecture for image segmentation. So the idea here is that you have the downscale and upscale paths and some skip connections in between to preserve some information from higher levels, higher layers in the network. And you feed into this network an original image and a segmentation mask. And then you try to predict this segmentation mask and use the artificial segmentation mask and the predicted one, to compute the objective function. Applied to diffusion approaches, it works a little bit differently. So here, our goal is not to predict a segmentation mask, but to predict an amount of noise in your image. And you may wonder now, like, why am I predicting noise if I want to create beautiful artistic images? And the idea here is that actually, if you predict noise in your image, you can then subtract it from your image. And by doing it iteratively step by step, you can arrive from a very noisy image to a beautiful artistic image. And the way how we train for that is as follows. So first of all, we start with an image an image. And we use some noise schedulers to artificially generate some noise and add it to the image. Then we try to predict this noise, and well, we use the artificially predicted noise as our ground truth for the objective function. And once you have trained your network, you do the inference in the following way. It's also a little bit different from the segmentation, where you just run inference once and then you get the result. In diffusion, you also run inference iteratively. And you start with a very, very noisy image, like on the top left corner on the image I'm showing you. And you do it iteratively, and you reduce the noise with every iteration until you arrive at a very nice artistic image. So it's fun. It's a very clever idea, and it works. However, the problem is that if you would like to generate images in high resolution, it will be computationally expensive. And if you want to make it more efficient, there is another trick. And this trick is called autoencoder, or precisely variational autoencoder in this case. So some researchers, they came up with this idea of encoding an image into the so-called latent space, where instead of performing all these diffusion operations, all these noise predictions in the original image, you first compress this image using an artificial neural network encoder into the latent space. It's basically a small image representation of your original image. Then you do all the noise prediction operations in this latent space, and then you use the decoder network in order to expand the image to the original size. And you can imagine that training this one is kind of straightforward, because what you get in the output is essentially what you would like to get in the output is essentially what is you're putting in the input. So it's a clever trick which allows you to save a lot on computation. And what I've presented you so far would also work even without the text model, but it will then generate you some random results based on the data set you've used for training. How do you control generation? Like, how do you use a text input in order to generate an artistic image of what you are asking for? And for that, we need the third component, the clip model. And the idea here is that we want to unify our text representation and image representation and bring them in the same so-called embedding space. And at first, we create embeddings from image and text, and they're different, well, logically, because these are different modalities. So how do we bring them together in the same space? And the idea here is to use the so-called contrastive loss function, where we compare the original embeddings from the image and the text using cosine similarity. And if they're similar, we are rewarding that. And if they are not similar, like in the negative pair, which we also need, we penalize that. And then we update the weights of our image encoder and text encoder accordingly. And this model clip, it's a model trained by OpenAI, and they've open sourced it, and everybody uses it these days. They have trained it on 400 millions of pairs of images, and these are images which have been crawled from the internet. And as the textual information, so it's kind of a supervised learning, because you need this text information to the image. The text information has been taken from the metadata of the images on the internet. So in the HTML, you have like alt tag, which has the alternative description of the image. So they use this image and alt pair in order to train this clip model, and now everyone is using it. And then, like, putting all the things together, we have our original image converted to the latent space. We have the generated noise, well, not generated, but artificially programmed. And we have our text embeddings. And then we use the so-called cross attention layers, which combine multimodal inputs in our unit architecture. And then we predict noise, which we then subtract iteratively from our inferred image. So it's a very cool technology, and that's how it works in a nutshell. You can also use image-to-image generation, and in the image I'm showing you, it's I draw it using my touchpad. And it was supposed to be a pink panther, but I knew I could do it even better. And I've used the Stable Diffusion model in order to generate a nicer version of it. But then I looked at this image and I thought, oh, well, maybe it looks like a cat, and I've generated a cat. And then somebody also looked at this image and said, no, it's a bear. I'm like, really? Okay, could be a bear. And then I've tried different things like monkey, cow, and even a pig. So yeah, I had lots of fun doing this exercise. And well, to summarize, you can have many use cases for image generation. So for unconditioned generation, and unconditioned, it means that we don't need the textual guidance. We can still use it. It can still be very useful, for example, for portrait synthesis, when you want to anonymize something and you want to use artificial people. You can use it for synthetic asset generation, like for populating of digital twins. So you want to create some 3D objects, or for super resolution to make your images look larger, and you can still use diffusion methods for that. And of course, for condition generation, there's text to image, there's text guided image to image, and there is selective image editing and inpainting. If you want, for example, to expand the scene and see what's there, what's hidden there behind the frame, or if you want to remove some person like your ex-boyfriend from your photograph, you just remove them and then use diffusion to fill the space. So there are many other use cases as well. And I'd like to finish my presentation also showing you our own diffusion model, which we call Edify. And the cool thing about it is that it is able to create text-to-image pairs, text-to-image results in high resolution, but it's also designed to create videos, temporally consistent videos, and also objects in 3D. And you can then get these outputs through the API in the so-called Picasso service, as we call it. And you can bring them the results from your model into popular editors like Photoshop, Premiere, PowerPoint, yeah. And you can also bring them to Omniverse to create digital twins like this one, for example. So it's really fascinating, and I think the possibilities are really limitless, and I'm excited to see what comes next.
Thank you very much, Katja. I must say that was a really interesting discussion, especially about the Omniverse stuff. Like, that was interesting to see related to the generative AI stuff. Now we'll move on and sort of offer the floor to any questions for Katja. I know that I certainly have a few, but if there's, I'll pass over to the audience first. If there's any questions from your guys' side, please do write it in the chat, and then I will ask Katja. We'll give it a couple of seconds. Cool. We've got a question here straight away from Mauro. He's asked, how expensive is it to run and generate such video clips like you showed at the end?
Well, for video clips, I must admit it's still not available for general public. We have it in our research, but to use it, you need to wait a little bit. So for expensive, it's expensive to train these models for sure, but generating, it's usually not very expensive. So you need a GPU for that for sure, but you don't need the whole cluster for that.
Cool. And just leading on to that question, Katja, when will that be released to like the wider public?
I can't share this information.
No worries. Any other questions from anyone else?
So I see here as an example, isn't this a latent diffusion model from Stability AI? It's a common misconception that Stability AI has introduced this model, because actually Stable Diffusion has been introduced by researchers from LMU in Munich. And then Stability AI, they did some clever marketing around it. But it's like, yeah, many people attribute it to Stability AI, which is not correct.
Cool. No worries. Thank you. I've got a few questions that I was sort of jotting down there as well, Katja. Just in sort of general, when it comes to generative AI, do you think that there'll be a point where we can trust generative AI for critical business processes?
For example?
So yeah, say for example, you have like a really sort of key decision that you need to make between a stakeholder internally within a company, and there's multiple opinions. You've got a split decision internally, and then you sort of opt to generative AI to try and give you the best possible solution. Do you think that we'll get to a point where we can also use generative AI for these sorts of decision processes?
So with AI in general, not only generative AI, I think like there is a common practice to believe that it's not a silver bullet for anything, but it's rather a companion. It's something which helps you to achieve better results. It helps you to be more productive. But we do not design systems in order to replace human. It also, for example, applies for use cases in healthcare, where like physician sits there, looks at the CT scans and tries to find cancer. AI will be instrumental and very helpful in these use cases, but we are not in the place to remove the doctor, because somebody needs to be responsible for the decisions, and we cannot make AI responsible.
Cool. Interesting. Yeah, I totally agree with the point where we do still need humans in the job. Like generative AI is great, but we also need to sort of put some limitations on it and keep to sort of a human process sometimes. Cool. I have another question as well. Like, what is the exploration of generative AI crucial for when expanding the boundaries of human creativity and fostering innovation?
Yeah, I think generative AI is super useful. And I also gave you a couple of examples like brainstorming, and you don't have the writer's block anymore. Like maybe artists can also get some inspiration and like sketches. Like I see also people in fashion use it to get some inspiration for their creations. I saw a couple of campaigns already, like of popular brands. Like I was working somewhere in some airport, and there was advertisement from Desigual, and I saw like these images look weird, and then I looked closer. They were AI generated, and they're basically like selling clothes which they have generated using generative AI. I thought it's fun.
Yeah, that is cool. A different concept for sure.
Yeah.
Cool. Has anyone got any other questions in the audience? If not, I've got an exciting competition that we'll move on to, and I'll give everyone a bit of an opportunity to enter at the last minute as well, if anyone would like to. We're going to be giving away some of Nvidia's self-taught courses, but I'll allow a couple more seconds or so just for any more questions towards the end. Cool. We've got one here from Skiff as well, Katja. So, what are some challenges when applying large language model like architectures to time series data as opposed to text?
Mm-hmm. Well, of course there are challenges, and well, text is also sequential data, right? So, and what you see here with the transform architecture, working with sequential data is a bit easier. They have these attention mechanisms inside of the transformer layers, where basically you can get the sequence of data and then differentially weight different parts of, like in this, like it applied to a sentence, for example. And I can think of a concept like that with time series data as well. I'm not an expert here. I come from computer vision background, but just logically thinking, I think it's transferable.
Cool. thanks. And Min's also asked a question here. So she said, so far the models have been created based on all data available throughout the www. In some more iterations, we will have much more training data in is created by generative AI. What kind of effect do you think that this will have on the future model qualities?
Yeah, it's a tricky question, I would say. So first of all, you need to understand, do you have the legal rights to use data generated by models which have been trained on different data? And so as far as I know, sometimes, well, now it's not allowed, like if the data is like trained on some general purpose. Will we see like any quality improvement in that? I doubt. If you only use like generated data, we need some real data for, at least for the models like this, for diffusion models. I am actually like a big proponent for synthetic data, but that's a different topic. But for diffusion models, I would say it's better to use real data. And well, it's not only like data which has been like so the models like Stable Diffusion, they've been trained on data which is freely available in www. But like, for example, we at Nvidia, we partner with stock companies like Getty Images, Shutterstock, and this allows us to create unique models. And with collaborations and partnerships like that, I think the future is really interesting.
Cool, thank you for that. And then we've got two more questions, and that will be the final two before we move on to the competition. So one from Dan here that says, how do these models perform in real-time detection scenarios? And are there any challenges in deploying these models for live monitoring of transactions or communications for fraud and spam detection? Interesting.
The models I've shown you were the models for image creation, but of course there are models also for detection in computer vision domain. And the performance wise, I mean, is the question about performance or accuracy challenges in deploying live monitoring? Okay. So communications, fraud, spam, it's a different modalities as well, and there are benchmarks. And well, for that, I would recommend you going on Hugging Face and seeing like what popular architectures for which use cases, what is their performance. But I can tell you that there are ways to optimize these models. Like we, for example, at Nvidia, we develop our TensorRT optimizing compiler, and recently we've also expanded it to large language models. So it's called TRT LLM, and the project is on GitHub. So it makes real-time execution possible for different use cases for different models. And we are expanding it to new architectures with time.
Cool. Thank you for that. And we've got Mauro here as well, who sounds like he's quite new to the standard learning architectures, which is great for someone like himself to learn from you, Katya. He's asked like, who are basically the biggest players and places where he can learn about more about unsupervised deep learning architectures?
There are many good places, and well, Unit is a supervised architecture, but there are many good places. And Deep Learning Institute by Nvidia and the courses you will give away now, actually, there are some good courses there. You can find lots of materials on YouTube in free access. There are good paid MOU courses as well. Check Coursera. Yeah, like back in the day, I was learning also using Coursera. So these days it's really really easy to get good content, good learning content, and talk to models like ChatGPT. They also know some stuff, but trust it, well, not always trust it.
take it with a pinch of salt.
Exactly.
Of course. But no, yeah, thank you for that, Katya. Like, really interesting talk. I know obviously seems like the audience really enjoyed it as well, so thank you for spending the time to speak about it.